For this problem, we want to identify any local minimums, maximums, or saddle points for this function. And the first thing we've got to do is we have to identify the test points. So what was the process there? How did we identify test points? What did we have to do? Well, we looked at the partial derivatives. We wanted the rate of change of altitude with respect to x, f sub x to be 0. We also wanted the rate of change of altitude with respect to y to be equal to 0. What does this give us? If I have something like this at this point, that would give me a horizontal tangent plane. And a horizontal tangent plane has a chance to be a minimum or a maximum. So that's what we're starting with. So looking at this, then, let's evaluate our partial derivatives. F sub x with respect to x, what do we get? 4x plus 0 plus 8 minus 0 plus 0. And f sub y, partial with respect to y of this is 0 plus 2y plus 0 minus 6 plus 0. And again, setting those partials equal to 0. 0 equals 4x plus 8. 0 equals 2y minus 6. Let's go ahead and solve that and see what we get. So negative 8 is 4x dividing by 4. We get negative 2 is x. Over here, 6 equals 2y divided by 2, 3 equals y. So what does that leave me? Negative 2, 3 is a test point. It's the only one we have. So it's our only candidate for a minimum, a maximum, or a saddle point. So let's collect the information we have to determine whether that point will be a min, max, saddle point, or possibly none of the above. So we need to find the second order partials. So for example, I need f sub x, x. That's the partial with respect to x of 4x plus 8. So fxx is 4. How about f sub y, y? That's the partial with respect to y of 2y minus 6. So f sub y, y is 2. We can also get f sub x, y. That is the partial with respect to y of f sub x. So f sub x, y is the partial with respect to y of 4x plus 8. And that's 0. So fxy is 0. Similarly, f sub yx is the partial with respect to x of f sub y. So f sub yx is the partial with respect to x of 2y minus 6, and f sub yx equals 0. Now, that shouldn't surprise you, right? We have fxy and fyx are the same. That will always be the case for the types of functions that we choose to study in this course. Now, from these second derivatives, we're going to build our Hessian matrix. What is that Hessian matrix? fxx, fxy, fyx, fyy. So plugging in those numbers, we get what? fxx is 4, then 0, then 0, then 2. And D is the determinant of the Hessian matrix, which is fxx times fyy, minus those two are actually the same. fxy squared, and I get 4 times 2 minus 0 squared, which is 8. So right now I have D is 8. That's going to be important to remember, as well as fxx is 4. That's going to be important to remember. So what's the technique we need to use to determine whether we have a minimum, a maximum, or a saddle point? So here are our rules to guide us in terms of making a decision. We determine the behavior of that test point by looking at the determinant of the Hessian, or D. So if D is positive and fxx is positive, the function will achieve a minimum. If fxx is positive, we think concave up from back in one variable calculus. Indeed, that's a local minimum if it's concave up. If D is positive and fxx is negative, we think it's concave down, and that has a maximum. And then if D is 0, the test is inconclusive, just like in Calc 1, if we had like f of x is x cubed inconclusive, or f of x is x to the fourth inconclusive on the second derivative test. But if d is less than 0, then the test point is a saddle point, which is an interesting kind of thing. Now, what do we have here? What was our case? So our test point was negative 2, 3. Our d was 8, and our fxx was 4. So d is positive, so we're either in the first case or the second case. The fact that fxx is 4 tells me that I'm going to have a minimum. So this means I should have a minimum at negative 2, 3. So let's take a look at a graph to see if that is the case. So there's our function, f of xy is 2x squared plus y squared plus 8x minus 6y plus 8. We believe there should be a minimum at negative 2, 3. It's looking pretty good for a minimum. Now, is that at the point negative 2, 3? Desmos tells me that if x is negative 2 and y is 3, the z value is negative 9. So let's take a look at that point, negative 2, 3, negative 9. And let's make it a better color that jumps a little bit more for us. We see we have that purple dot at negative 2, 3, negative 9. That looks pretty good. And then we could also draw in the tangent plane. The tangent plane with z equals negative 9. And we can see from that that indeed that is the tangent plane to the surface. So the rate of change with z with respect to x is 0. The rate of change of z altitude with respect to y is 0 at that point. So indeed, the f sub x equals 0, f sub y equals 0 is true. That is a test point. And we can see from our d, our determinant of our Hessian matrix, that that thing is a local minimum.